cosmic enigma unveiled. The night the heavens shone jade. On September 7, 2025, the globe gazed as the moon slipped into Earth's shade. Yet what truly amazed stargazers surfaced soon after. The firmament blazed vivid jade from skyline to skyline. Hobby astronomers snagged a flashing frosty sapphire comet that inexplicably morphed into a radiant jade hue, lingering even beyond the eclipse's close, online forums. Spun into turmoil as specialists raced for insights. That evening marked the debut of 3-2 Atlas, our third cosmic wanderer zooming past Mars at 98 kilometers per second, carrying secrets no Earth observatory was ready to unravel. Why would a comet from a distant star system bathe our skies in a shade? Science struggles to fully decode. Hours post-eclipse, initial snapshots flowed from backyard scopes in Buenos Aires, Nairobi, and Lisbon's edges. In raw captures, a faint blue trail sliced the shadowed heavens, its tone deepening to a vibrant jade that held firm even as the moon broke free of Earth's umbra. In Sao Paulo, a learner with a borrowed DSLR nabbed the hue shift in a flurry of 10-second exposures. Timestamps pegged to 0318 UTC, aligned with a surge in hobbyist chatter. Never seen that jade shade enduring after the eclipse. The hue, the pace, it's shouting, not local. In Cape Town, a retired technician tracked the object's angular shift through a 6-inch Newtonian, noting a speed so swift that mere minutes between shots showed clear movement against the starfield. The comet's visible motion, nearly a quarter-degree hourly, defied norms for any known solar system guessed. Across Europe, skywatchers swapped notes on the lasting jade glow, debating filters and tuning, yet raw data told the same tale. The jade persisted, unyielding under urban glare or fading with the moon's return. In the hours that followed, forum threads swelled with uploads, stacked visuals, spectral traces, hand-sketched drawings, metadata flooded in, coordinates, exposure durations, filter bands. A rural Turkish educator shared a time-lapse capturing the hue shift frame by frame, while a Moroccan high school club measured the comet's position drift against backdrop stars, confirming its blistering speed. By dawn, the proof was global and undeniable. The object's hue and velocity were unlike any comet in living memory. Hobbyist networks, often slow to align, united on one verdict. This was no ordinary traveler. The world's experts, still silent, braced for a data flood they couldn't ignore. By 0700 UTC, the phrase, "night the heavens turned jade," had become a hashtag. Global telescopes from backyard rigs to 10-meter titans now aimed at a lone swift jade visitor. The shift from public wonder to scientific urgency was complete. Time was ticking, every moment counted. Inside the Atlas Control Hub on July 1, 2025, the first data batch from Rio Hurtado sparked a routine script. Run the detection through the orbit calculator, check known asteroids, flag anything odd. But the software faltered. Each try to fit a closed elliptical path spat out errors that would settle. The figures pointed to a trajectory that didn't loop back, didn't belong to our sun. Eccentricity above 1 hyperbolic. Not just a statistical quirk, but a mathematical wall. A small analyst crew gathered around the screen, watching errors climb with each tweak. Standard rules urged waiting. Gather more data. Rule out false detections, avoid clogging the verification pipeline with mistaken alerts. But the object's apparent speed and path kept breaking the Model A log. Entry at 0314 UTC captured the unease. If this holds, it's interstellar. If not, we waste global time. One analyst, recalling the frenzy of Oumuamua's discovery, pushed for escalation. The Minor Planet Center was pinged, flagged with an urgent note. Fit unclosed eccentricity above 1 possible ISO candidate. The hub's debate shifted from caution to calculation. How many hours until follow-up became impossible? Every lost minute shrank the window by 0500 UTC. The team moved as one, prepping the alert for global release. The interstellar banner was raised. For the third time in history, the software couldn't bind the orbit to the sun. The Minor Planet Center alert, issued at 0512 UTC on July 1, 2025, stamped with the object's initial label and a warning: orbit fitting failed. Eccentricity above 1, outbound velocity unbound. Within hours, the object earned a formal name, 3-2 Atlas III, confirmed interstellar object after Oumuamua and Borisov datasheets told the tale in numbers. At discovery, 3-2 Atlas was already moving at 61 km per second. Trajectory models projected a perihelion speed nearing 98 km per second. That's fast enough to cross Earth to Moon in just over an hour, far beyond any probe rocket or planned interceptor's reach. Orbit dynamics specialists, some who'd modeled hypothetical extrasolar travelers for years, watched errors climb in real time. The hyperbolic path was clear. This was a one-time flyby, a cosmic dash that wouldn't repeat. Official notices flowed. Cease 2025 N1 Atlas, reclassified as 3-2 Atlas tagged interstellar, and added to the short exclusive list of solar system intruders. The impossibility of pursuit settled fast. No existing mission, not even the swiftest solar sail concepts, could match its velocity or path. With the closest approach to Mars set for October 3, 2025, at nearly 29 million kilometers, the window for deep study was vanishingly narrow. The notification process, once routine, now sparked a global rush for remote observations. Every telescope, every spectrograph, every available eye was needed before 3-2 Atlas vanished forever. Spectrographs from La Palma and Gemini South streamed data before sunrise, their raw outputs scoured by gas phase analysts seeking the familiar trace of C2, the molecule behind the classic green glow in nearly every recorded comet. But the data spun a different story. Instead of sharp swan bands near 516 and 563 nanometers, the jade region showed a broad, featureless expanse. Line by line, the expected diatomic carbon signature was missing. Infrared scans added another shock. Carbon dioxide, not water-dominated CO2, outstripped H2O by a factor of 8, a ratio unseen in inner solar system comets. The usual water-driven chemistry was upended. Cyanogen, a molecule sometimes boosting blue-green tones, appeared in modest amounts. Carbonyl sulfide barely registered. Neither could explain the jade emission's intensity or persistence. In control hubs, specialists swapped theories in real time. Some pointed to dust scattering, but polarimetric data countered a simple answer. Others sifted lists of rare radicals and exotic volatile compounds, yet none matched the observed hue. C2's absence left a chemical void at the anomaly's core. For now, the only certainty was 3-2. Atlas had rewritten the hue playbook. The jade glow was real, unmistakable, and by every standard measure, unexplained. Spectrographs from the globe's largest telescopes began revealing an unexpected signature. Over 20 distinct nickel lines, several in the ultraviolet, stood out with clarity, leaving little doubt. Iron, typically paired in comet metal emissions, barely showed. A few weak lines, some at detection's edge, most missing entirely. The ratio was so skewed that in some frames nickel outshone iron by a factor of 50 or more. For comet chemists, this was a chemical imprint from other realm lab teams. Some, still running overnight cryochamber tests, scrambled to match the spectra. Nickel carbonyls, volatile at temperatures colder than any solar system. Comet became the prime suspect. In labs, these compounds sublimate at -25 degrees Celsius. But in the deep interstellar void, they might linger billions of years, waiting for a stray star's warmth to trigger release. Iron, by contrast, tends to lock into silicates or heavy grains, tough, refractory. 3II Atlas scattered light with deep negative polarization, a pattern seen mostly in the outer solar system. Trans-Neptunian objects, not inner comets, paired with early Hubble imaging, suggested a compact nucleus, likely just a few kilometers across, wrapped in a CO2-rich coma. The physics of this dust, tightly packed submicron and unusually cohesive, hinted at a birthplace far beyond the frostline of any ordinary star. For planetary scientists, the stakes were sharpened. The chemistry wasn't just exotic. It was a direct clue to how planets and comets form in the galaxy's coldest reaches. The clock ticked for lab replication. With Hubble and JWST soon blinded by the sun, all eyes turned to Mars orbiters for a final shot at capturing metal vapor and dust physics before 3-2 Atlas vanished into deep space. Mars became the fallback, with Hubble and James Webb Space Telescope blocked by solar elongation. The only way to catch 3-2 Atlas during its critical pass was from orbit around another planet. The Mars Reconnaissance Orbiter and MAVEN, both deep in their own science missions, faced a sudden, high-stakes retasking order. On September 10, 2025, a classified memo from NASA's Planetary Science Division hit mission managers' inboxes: prepare for a target of opportunity campaign effective immediately. The object would sweep within 29 million kilometers of Mars on October 3, a distance close enough for high-resolution ultraviolet and infrared instruments to dissect its coma and tail, but only if the window was seized. The politics were intense. Mars climatology teams fought to keep their seasonal data uninterrupted, citing years of baseline measurements at risk. Engineers hustled to rewrite targeting software, reposition sensors, and negotiate observation slots with international partners. Congressional science committees weighed in, demanding the unique interstellar event take priority. In the end, the Science Division broke protocol, pushing full approval in just 48 hours, a process typically dragging weeks. By September's end, the Mars outpost was on alert. Instrument teams rehearsed rapid-fire observation sequences, knowing the comet's speed, nearly 98 km per second at perihelion, left little room for error. On October 3, as 3-2 Atlas made its closest pass, both orbiters captured spectra, ultraviolet flashes, and atmospheric readings impossible from Earth. In 3 hours, MAVEN returned more data on metal vapor and coma structure than most missions gather in a season. The gamble paid off. Mars, for a brief window, became humanity's sole eyes on an interstellar visitor. In late 2025, software engineers at TESS and Rubin Observatory faced a harsh truth. 3.2 Atlas slipped past their algorithms not once but twice. Archival frames from October 2023 and June 2024 showed faint, fast-moving traces barely above noise. But real detection pipelines tuned to filter out hyperbolic or color-odd candidates to avoid false alarms had quietly discarded the signals that mattered most. The post-mortem was swift and unsparing machine learning. Developers, some still sifting old logs, began rewriting code to flag outlier paths and jade-leaning color bursts in real time. The new mandate: no more missed interstellar visitors, even if it meant more false positives. And late-night calls. Mission architects watching the data review pushed for a bolder fix. If software can't ensure early warning, hardware must be ready to launch instantly. Proposals for rapid response interceptors, solar sailcraft, modular instrument swarms, even disposable CubeSats moved from whiteboards to funding decks. Technical specs were ambitious. Launch within weeks, ride solar pressure to match hyperbolic speeds, and swarm inbound objects with sensors before they vanish. NASA, ESA, and private teams weighed rival blueprints, each promising the agility 3.2's Atlas exposed as lacking. For the next visitor, the plan is clear. Survey triggers activate on odd hues and unbound orbits. Interceptor fleets stand ready not just to observe from afar, but to meet the next interstellar messenger halfway. The lesson of 3.2/Atlas is etched into every code line and mission concept. Cosmic surprises demand preparedness, not regret. In October 2025, 3.2 Atlas passed within 29 million kilometers of Mars, its closest approach captured by Mars orbiters after Earth telescopes went offline. Confirmed as only the third interstellar object ever detected, its 98 kilometers per second perihelion speed and hyperbolic path were verified in Atlas and Minor Planet Center records. Spectra revealed intense jade light, yet the classic C2 swan bands were absent. Instead, carbon dioxide dominated over water by 8-1, and over 20 strong nickel lines appeared without matching iron-breaking known comet patterns. Despite global observations and urgent data collection, the true chemical source of the jade glow remains unsolved. Archival tests and Rubin data showed early traces missed by older software, prompting survey upgrades and mission proposals for rapid interception. 3.2/Atlas has departed, but its anomalies set a new standard. Every interstellar visitor brings unique clues about planetary origins, and readiness hinges on what we learn from each.